Hello, I'm Helen Duncan and I'm here at Plextek RFI interviewing Devlin, the CEO. It's October the 13th, 2015 and we're going to be talking about 5G. Liam, why do we need 5G? What is it going to do for us?
Well, the aim is to offer the user the perception of near infinite capacity, together with low latency and uniform coverage over a wide area, as well as providing improved performance for all of the existing applications. For example, downloading a HD movie in less than 1 second. The technology will enable and encourage the development of new applications and markets and technologies, and it will include an increasing number of machine-to-machine applications.
These sort of download speeds will clearly require a step change in data rates. How's this going to be achieved?
Well, that's right. Some of the demands can be met with the new interfaces being developed for the existing cellular bands below 6 GHz. However, the main advance will be to use much higher data rates, and this is practical with much wider channel bandwidths. And the way to achieve this is operation at millimeter wave frequencies where the required spectrum is available. The cell sizes will also be small. Around about 200 meters is considered the maximum. This will allow increased capacity on the network, and it will also make the use of the millimeter wave frequencies more practical.
Millimeter wave frequencies have traditionally been associated with point-to-point links. What's changed to make them suitable for non-line of sight applications?
That's very true. A number of research programs involving extensive propagation measurements at different millimeter wave frequencies carried out around metropolitan areas in various places around the world have shown that the issues associated with using millimeter waves for non-line of sight communications can be addressed and overcome. Now, they did this by employing adaptive beam steering at either one or both ends of the link. Now, in a practical millimeter wave 5G system, I think some form of electronic beam steering will be used, such as electronically steerable phased arrays.
A millimeter wave phased array sounds complex and expensive. Is it going to be practical?
It does, I admit, but yeah, I think it will be practical. In the mobile device, I suspect we're looking at a modest number of antennas, 60 maximum, perhaps as few as 4. In terms of whether to use digital beamforming or RF beamforming, this is still hotly debated. Now, digital beamforming gives you a lot more flexibility, but there is concern that it will be difficult in practice because of the very wide channel bandwidths. The base station will need to communicate simultaneously with multiple mobile users. And at the base station, an alternative approach might be used to that which is used at the handset. For example, a small array of electronically switched fixed sectorized antennas. At the moment, there are a lot of trial programs underway investigating these different approaches and trying to work out which ones will work best in practice.
When are we going to know which millimeter wave bands are going to be assigned for 5G?
Well, the first systems planned to be launched as 5G will actually be the sub-6 GHz frequencies. In actual fact, the final decisions on the millimeter wave bands won't be made until the World Radio Communication Conference in 2019. However, before then, there'll be lots of coexistence trials, a lot of debating, and people will discuss the relative measurements of the various candidates. In terms of candidates, E-band, that's 71 to 76 and 81 to 86 gigahertz, that looks attractive because there's a lot of spectrum and it's potentially available on almost a worldwide basis. A number of E-band trials have been run, and indeed still are being run, and they've shown some promising results. There's also a lot of interest in Ka band systems, and again trials have been implemented and been successfully conducted at Ka band, particularly around about 28 gigahertz. And whilst Ka band does ease the implementation issues with the millimeter wave electronics, the downside is that the same spectral allocation is unlikely to be available worldwide, and so some sort of regional licensing is probably going to be necessary for Ka band. There are also some organisations who think that a composite system is the way to go, so that's combining communications both at millimeter wave and in the sub 6 gigahertz band.
You've discussed electronic beamforming as a solution to non-line of sight. What about massive MIMO, which is also being talked about as a candidate for 5G?
It is, and I think massive MIMO will be more practical for the 5G systems that operate below 6 gigahertz, because at these frequencies there is a much richer multipath environment, and by that I mean that the multiple propagation routes that are necessary for MIMO to function effectively are more usable at these frequencies below 6 gigahertz. I think if MIMO is used for millimeter wave 5G, it's likely to be relatively modest implementation, maybe 2 by 2. I think that massive MIMO at millimeter wave is unlikely.
The other consideration, of course, is how good will the indoor coverage be for 5G?
In honesty, I think the 5 millimeter wave 5G, the indoor coverage will be almost non-existent, because the attenuation through building structures at millimeter wave is a lot higher than at RF frequencies, the sort of traditional RF frequencies we've been using for 3G and 4G. So if we imagine a 5G system, when a user moves from an outdoor environment to an indoor environment, they'll switch either to a Wi-Fi connection or a 4G connection. Of course, this switching must be seamless. The exception is likely to be large public buildings and office spaces where additional 5G small base stations or distributor antenna systems can be installed to extend the 5G coverage.
Thank you very much.
Thank you.